Hello everyone, welcome back. Welcome back to outcome-based regression channel. So in the last video, we have seen how to load the data for classifying the images using the wavelet-based features. So in this video, we will see how to extract these features. So what kind of features will be there? How to extract the features in the outcome-based education channel? We will see in this video. So here we have imported the modules numpy and PyWT. This PyWT is belonging for extracting the wavelet transform features. And this is CB2 is belonging for OpenCV modules. So here this matplotlib we have imported for displaying the images and as well as graphs. This already we have seen in the last video. And now for extracting the wavelet features, first we need to understand what is wavelet transform. This wavelet transform is a multi-scale and multi-resolution transformation. It can extract the image features like high frequency and low frequency components. That means when you have an input image, this input image will be given as input to the wavelet function. This wavelet function will divide the entire image into 4 different components. One is approximation, and another one is horizontal, and another one is vertical detail and diagonal details. So that means approximation component will have all the low frequency components, all the low frequency image coefficients will be available. In horizontal detail, will have horizontal edge information. High frequency is nothing but like a edge information. So vertical detail means it is having the vertical edge information, and the diagonal detail means the diagonal edge informations. So all these things we will have in the wavelet components. So next we have to apply the wavelet transformation. For that PyWT dot DWT2. This DWT2 is representing the discrete wavelet transform 2-dimensional. Here we have to pass the input image and what type of wavelet we are going to apply. There are different wavelet families like Haar wavelet, Dabuchis wavelet, biorthogonal wavelet. Different versions of wavelets are available. If you are familiar with the image processing concepts, you can easily understand the different kind of wavelets. In each wavelet, there are some advantages for going the higher versions of wavelet families. So Dabuchis wavelet is the basic wavelet everyone easily can understand. So it will perform a good function for extracting the approximation, horizontal and vertical detail coefficients. So after applying this function in the COEF2, COEFFS2 is the variable which is holding all these 4 coefficients of the input IMG variable. Okay, so now from this COEF2 we have to divide this approximation, horizontal, vertical and detail coefficients. So in this COEF2 itself there are all 4 coefficients will be available. So now this LL is representing the approximation, LH is representing the horizontal, HL is representing the vertical and HH is representing the diagonal. Okay, so now the wavelet transform working principle I will do in the separate video. If you want, you please comment below. Otherwise, only for applying purpose for extracting features, this function is enough to understand. Okay, now I will show, I will display the wavelet coefficients like LL, LH, HL, HH. So here again I am importing the matplotlib thing. Matplotlib I can import, and after importing the matplotlib, I need to define the size as I mentioned in the earlier. And next we have used the for loop for getting each and every coefficient LL, LH, HL, HH as the list. I am enumerating the list of 4 coefficients of wavelets, and each coefficient will be stored in the A. Okay, now I am just dividing the entire display as subplot. So in one row 4 images will be displayed. 1 comma 4 means one row 4 images will be displayed as shown below here like this. If you want in 2 rows, you can mention 2 comma 2. That means in 2 rows, each row 2 images will be displayed. That is how you can divide the screen for image display purpose. So here im show is the function that I can use to display the images. So im show in the axis, in each axis I can show some different images. Im show a is the image. So the for loop will be iterate for all the 4 coefficients. So 4 times for loop will be iterate, and each time this a will be displayed. Each time this a will be displayed. Okay, so this is how we are showing the all the 4 images. We'll run this code. First we have to create the list of approximation, horizontal, vertical, detail. These are the labels. Just I have given labels of the 4 wavelet coefficients. After that we need to apply the wavelet transform by wt.dwt2, and next divide all the LL, LH, HL from the coef2 and apply the for loop for displaying. So this is how you are getting. See, in approximation you are unable to see here anything because it is only having the low frequency components. There is no much variations in between the pixels. So you will be not able to see here any variations. But in horizontal you will get horizontal edge information, and vertical you will get the objects about the vertical edge information, and diagonal edge information you will get in the diagonal detail coefficients. So after that extracting the wavelet features, we are extracting the heraldic texture features. See, here in feature extraction there are different features like texture features, color features, and shape features. But if you come for the texture features, these texture features are nothing but the representation of pixel arrangement in the image. The representation of pixel arrangement. For example, if you see the tiles arranged in our floor, so all the tiles will be arranged as squares side by side like a chessboard. So the chessboard pixels are arranged in white, beside that black, beside that white. That is the arrangement of chessboard boxes. So like that pixels also will be arranged in a particular pattern. Based on that only you can identify the object. Okay, the texture is most important feature if you want to detect any object. So for example, if you go to the previous image, here the aeroplane pixels are arranged in this way. This is representing the texture of the aeroplane. See here, all the vertical detail coefficients are representing the aeroplane texture. Okay, so like that you can identify some object based on the arrangement of the pixels. So this is what texture. Okay, so there are so many ways to identify the texture. There are Tamura texture features, Gabber texture features, like that. Here we are using the very easiest method, heraldic texture features. Okay, I'm not going to explain in this video what is heraldic texture feature and all. So here I am going to explain how to extract this heraldic texture features using the MATLAB, I mean using the Python program. Okay, so here we have in this SK image module, we have a feature, and in that we are having the heraldic texture features using the Greco matrix and the Greco probes. So this Greco matrix is gray level co-occurrence matrix. How the pixels are occurring, how the pixels are occurring represented. That matrix we have to identify. After that we have to extract some properties from that arrangement. First we need to identify how many, for example, you see this image, how many blue color pixels are available side by side, how many red color pixels are available side by side. Like that we have to extract the gray level co-occurrence matrix. That means each pixel occurring how many times in either in diagonal or horizontal or vertical. Okay, after getting that information you need to extract some properties. The properties are nothing but like a statistical properties like the mean, energy, entropy, standard deviation, like that we can extract. So this heraldic is the author who derived around 13 features for representing these properties of the gray level co-occurrence matrix. Okay, so these two properties we have to import, and next just again I have applied the wavelet transform again on the second level. Second level means already we have a wavelet transform we have applied and we got the LL, LH, HL coefficients previously. On the LL, again I am applying the double cheese wavelet to two-dimensional double cheese wavelet uh, discrete wavelet transform I am applying on the LL coefficients. So if you apply again, more number of features will be extracted from the only approximation coefficients. Okay, more high dimensional, more edge information will be extracted. So this is how we can represent after extracting. So it is just still running. We'll wait and see for few seconds. So you will get after implementing the this wavelet transform on again second level, you will get the coefficients. Okay, like this. See, again we have extracted more edge information from the approximation coefficient. See, this is the difference between here vertical and here aeroplane vertical coefficients, and here this diagonal vertical coefficients are different. So now if you understand, you can extract this gray level co-occurrence matrices for all the 8 coefficients. Why 8 coefficients? Already here approximation horizontal, vertical, diagonal in the second level wavelet, and we are having approximation horizontal, vertical, diagonal level coefficients in the first level. So total 8 coefficients are there, and for 8 coefficients you can extract the gray level co-occurrence matrices in the all four dimension, like 3 RGB images are there, for example. So 0 is the R channel, red channel, green channel, blue channel, like that. So 8 into 3, total 24 gray level co-occurrence matrices we have to compute. Okay, so total 24 gray level co-occurrence matrices are computed and appended to the variable G. This is how we have computed. So for applying the gray level co-occurrence matrix is very easy. Gray co matrix function, and we have to pass the image as the numpy array, and I am just converting into numpy array, and we have to give the direction like in horizontal or vertical, like that. And next, how many levels of gray levels, that means how many color pixels are available from 0 to 255. 8-bit image I am taking, so 256, 2 power 8, 256 gray levels will be there. Okay, so symmetric and normalized. So all these things you can understand after studying about the gray level co-occurrence matrix. These are just parameters, optional. If you are giving or not giving, the gray level co-occurrence matrix function will be executed and you will get the result. After executing the gray level co-occurrence matrix, you have to extract gray level co-occurrence properties, gray co-props. So here I am extracting 4 important features. These 4 important features are available in many research articles, so that you can easily, they have frequently used. They are giving more accuracy than the other features. That is why I have taken. These features are contrast, energy, dissimilarity, and homogeneity. You no need to write any formula here. You just have to mention the property name. There are 13 features available. In that I am only extracting 4 features, very important features from the image coefficients. So you have to pass here gray level co-occurrence matrix. You have to pass gray level co-occurrence matrix. So there are 24 gray level co-occurrence matrices are available. So what I am doing, I have taken a for loop, and each and every gray level co-occurrence matrix I am reading into T, and like G of T means first gray level co-occurrence, second, third, like that. From each gray level co-occurrence matrix I am extracting all the 4 properties. Okay, so after extracting, I am just doing the reshape, because a feature dimension for each image we are having the feature dimension in the single vector. That is why I am just reshaping into the single vector. I will show here, then you can understand. For example, image 955, all these are the features I have extracted. So there are 96 features I have extracted. Okay, but for sample I have saved 16 features in the ml feature 1.csv file. Okay, that csv file I am loading and I am extracting here. So here 0 to 15 total 16 features are there, and the 16th column is represented by the class label. Okay, here 995 images belonging to coastal mansion. Okay, so this is how I have saved all the features in the ml features1.csv file as my feature data. So like that you can extract the features and you can save into the one csv file, and whenever you want to do for classification or something, you can easily do the classification by loading this csv file. For loading the csv file, this pandas module will be very much useful. pd.read csv function we have to take here. If you give header none, then there will be no header read. The first line it will ignore just in the csv file. Okay, so now I'll show how to do some minimum classification. So this also we have seen in the previous video, mapping the class labels. So we have to map each class label with the numerical value. So here aeroplane, basketball, like that total 10 classes are available. So 0 to 9 labels are mapped. So 0 label is representing the aeroplane class, 1 label is representing the baseball class, 2 label is representing the basketball court. So like that we have to represent all the 10 classes to the each and every corresponding label. Okay, so after that what we need to do is, we have read this information into the features db variable. See, we have read this csv file into features db variable. In that features db, the 16th column is representing class labels, right? So what we are doing, this 16th column we are mapping with the changed numerical values. Instead of coastal label, you will get the coastal mansion, you will get 9 there. Instead of aeroplane in the 16th column, you will get 0. Okay, like that. So we are replacing the 16th column with the numerical values like this. See, if you display the head, you will get aeroplane is the 0th image. So the aeroplane class is mapped with the 0 label. This is what we have done in the previous code. All are simple only, but you need to understand the procedure, step by step procedure. First we have loaded the images, then we have extracted the features, and then we have done the numerical mapping for the features of the labels. And now we need to split into the test and train. See, in every data set in machine learning, we have to train. Based on the training only, you can predict the future features, upcoming features, you can new features, you can predict what kind of class it is. Okay, so for example, now uh, I want to split it. So how to split means you have to use train test split function. You have to use it, will be available in the sklearn cross validation, sklearn dot cross validation module. There you will have a function called train underscore test underscore split function. So if you give the input x comma y, this x comma y is what? X is holding the 0 to 15 feature values. Okay, y is holding the labels. So in this data up to 15 we have dividing into the x variable, and only the labels, the output labels, we are dividing into the y. So output is holding in the y variable, input is holding in the x variable. Okay, so now this x and y we are giving as the input to the train test split function. Okay, now another parameter you need to mention, test size. This test size is 0.3. That means 30% of the entire data. For example, you are having 1000 images. In that 30% means 300 images you are going to taking as a test size. So 700 will be for training, 300 will be for testing. Okay, random state 0. So randomly selecting some images. If you give 0 means it will select sequentially. If you give random state true, then it will select the this 300 images will be in 300 images will be selected randomly. Okay. Now after doing this splitting the testing and training, then what we need to do is we are standardizing the data. This is nothing but normalizing the data. The standardization means, wait, here I have not executed these files. I just only explained. We have to execute each and every module, then only we will get a errorless code. Okay. So I just explained and forgot to execute those lines. So now I am executing. So now we have to divide the values x and y and the shape of x. Now in the x we are having the 1000 rows and 16 columns. That means 16 features and 1000 image features. After that we have to split. So this has been splitted, and now standard scalar. This standard scalar also available in sklearn dot pre-processing. This is the pre-processing step for the features. Now you are having different features, but all these features may not be normalized. That means, for example, the mean distance between each and every feature will be varying. If in that case, you cannot give the proper predictions without normalization for the new features. For that purpose, what we are doing in the standard scalar function, this mean will be divided from each and every feature. That means it is becoming a zero centric mean. Okay. So let me explain you clearly. From 0 to 15, so many values are there. So if you find out the mean by adding 3.25 plus 13.7 plus 29.9, like that, so on up to 0.473 by 15, sorry, 16 values, right? By 16, if you do, you will get a mean value. That mean value will be divided from each and every feature. The zeroth feature by mean value, first feature by mean value, second feature by mean value. So if you do like that, it become a zero centric mean. So you will get a you will get you will get the like same mean will be there between each and every feature. Okay. So after doing this pre-processing for the X training and X testing, because we have divided into X train, X test and Y train, Y test variables. So 70% data will be available in X train and 30% data will be available in X test, and Y train, Y test also correspondingly divided. But we are no need to do any standard scalar for the Y train and Y test, because in the Y train and Y test you are only having the output labels. You no need to divide the mean from that features. Those are not features actually. Those are only output labels. Okay. Now we can see after doing the standardization, you no need to check this shape actually. Okay. Now we are doing the principal component analysis. This is also a most important pre-processing. This principal component analysis will be also available in sklearn.decomposition. In the module PCA will be available. This principal component analysis will work based on the eigenvectors and eigenvalues. So these eigenvectors and eigenvalues we can compute on the input data. So based on that, what will happen? It will give you the most variance of features. The variance between each and every feature vector it will compute, and if the variance is less, then it will remove from the features. We can remove some features. because if all the features are similar, you no need to have 100 features. So the whatever the most variant features are available, those features only we need to compute for our classification purpose. Okay, for example, I can say if you are seeing a human face, in that face, these eye features if you extracted, and most of the features are similar for left eye also. So you no need to save all the features for left eye, all the features of right eye. There will be some features having more variations between the left eye and right eye. Those features only if you can use for your discrimination to identify what is the differences, that is enough. The similar features you no need to consider. Okay, so the if the similarity is more based on the variation, okay, covariance matrix under it will compute based on the variation, it will reduce some features. So from out of 16 I am only considering the 10 features. Okay, so I am reducing 6 features here. So now you can compute this. So the shape of the, sorry, again, yeah, the shape of the training standardized data, if you see 700 in the input and 10 features instead of 16 features, I have reduced it to 10 features. Now the final point. So in perceptron model, this perceptron model is the basic like a hello world program in the machine learning or artificial intelligence. So you how to execute this classification models. Okay, for example, sk learn package dot linear model, you are having the perceptron model. First you need to import the model. After importing the model, this accuracy score and this precision recall are the performance metrics we will see later. But first, how to execute this perceptron model? So first you need to call the perceptron model constructor. In that constructor perceptron, you have to pass the eta value. This eta value is nothing but learning rate and random state. Randomly you can pick the input values for the training, or sequentially you are picking. So that random state is equal to 0 and learning rate is 0.01. See, maximum the learning rate represents very small value, either 0.01 or 0.001. Because if you give a small learning rate, it will train more accurately. But if you give very small learning rate than required, even if you give 0.001, the accuracy will be only 80%. You no need to give 0.001 because it will take lot of time for training if you give very less learning rate. So based on our practical experience, you can understand what kind of learning rate will be given for what kind of data. Okay, so now this constructor you should call with this eta and random state parameters, and this ppn object will be created. Now in this perceptron neural network model, you need to call a fit function. This fit function will be for training. In this train, what you need to do for training any model, you have to pass x train, I mean input data, training input data, standardized x train, and y train. Y train is only labels. Okay, first up to 0 to 700 labels. This x train std standardized training information from features from 0 to 700. In 0 to 700 features you are having up to 10 features only, not 16. We have reduced by using the PCA. Okay, so now why predict this? After training completion, you need to predict the new features. What are the new features available? Where in the test variable new features are available, so you have to give the test. So if you understand these 3 steps, you can run any kind of classification example. So perceptron, for example, you are classifying random forest, you have to import the random forest classifier. Then you have to call the constructor of the classifier. Whatever classifier you are using, you need to just call that classifier, that's it. Whether it is a perceptron or svm or logistic regression, anything, you have to import that classifier, then you have to call the constructor. Minimum two parameters you have to use, that is eta value and random state. And next you have to train this model by calling the fit function. You have to train this model by calling the fit function. In this fit function you have to pass two parameters. One is training input and training output. This training input is having the feature values and training output is holding the output labels. After training completion successfully, you need to use a predict function. This predict function, you have to pass only test information. You should not pass the output labels because already the training completed. Without giving what is the label for that feature, it has to predict what kind of label it is based on your training. That is what we can show the accuracy, how accurately it has predicted. Okay. So first we'll run this. So completed training and everything. Now you need to check the accuracy. How to check the accuracy? So in X text, we are having the testing features. In Y test, we are having the testing labels. So this Y test is holding the actual labels of the X test variables. I mean X test features. Okay. Those who have you have predicted, those features you have predicted from the X test is available in the X test variable, and the corresponding output labels are available in the Y test. Okay. And this Y pred is what? This is not actual labels. These Y pred are available predicted labels based on your training. So actual labels are available in the Y test. Predicted labels are available in the Y pred. So you need to pass these two variables Y test and Y pred to the accuracy underscore score function. Okay. Accuracy underscore score function you have to pass. So based on that you will get some value. That value will decide how much accuracy you are getting. So 80% accuracy you are getting here for your perceptron model. If you go next level, any other classification like logistic regression, any other classification like SVM. So whatever classifier you are using, the accuracy may be affected based on the model you are using, but the process is same. Okay. So you see for logistic regression application, simply sklearn.linear model importing the logistic regression classifier. I mean, it is a regression model. And next, what I am doing, I am calling the logistic regression, this one constructor, and I am not passing the eta value here. That means the learning rate it will take automatically based on the default value. Okay. Next, I am using the fit function. In the fit function, I am passing the training data, and Y train is the output labels. And after that, I am using the predict function. And now you can call the accuracy. So in logistic regression, I am getting 90% accuracy. So this is the simplest way how you can start learning with the existing models. Okay. The first thing you need to understand in this video, you can understand how to extract the features. In that features, how to extract the texture features. After extracting the features, how to train them with the existing models like a perceptron or logistic or SVM. So this is the simple video for starting your basic neural network programs. I think everybody understood. If any doubts are there, please kindly comment below.